appreciate very much your attendance. And today I'd like to talk about the development of X-ray detectors for spectral photon counting in radiology. And I present a presentation outline where I would like to talk about three different particular applications in radiology: CT, DEXA, or dual energy X-ray absorptometry, and also mammography. And in going over these applications, we'd like to talk about the ranges and resolutions that are required for the applications and show how new detectors are able to count individual photons and bin them according to energy in these applications, and this was previously unachievable. And for ranges, I want to define two types of ranges. One is the energy range, often called the dynamic range, and another range is the output count rate range. And for the resolutions, I'd like to talk about the energy resolution and the spatial resolution. In talking about the dynamic range, in conventional radiography, which uses energy integrating detectors, the dynamic range includes both the number of photons and their energy, since this is integrated into the detector. But with single photon counting, these two ranges are separate. And so since the beginning of the detection of X-rays, all of the devices that we've used to detect X-rays, starting with film screen systems, all the way up to the digital detectors that are used in digital radiography, the energy is integrated and we measure just the intensity. Modern digital radiology detectors often use either a scintillator or a direct conversion semiconductor, but that charge is then integrated and the signal is in terms of the intensity. The novel detector technologies I would like to use to replace these systems count individual X-rays and are able to bin them according to energy. This is done in direct conversion semiconductors, which convert photons into electron hole pairs, which are then collected across an electric field bias. And there's many reasons why this is of value. One of the reasons is because the attenuation curves are energy dependent, as shown here. I show a graph here of iodine, gadolinium, and bismuth mixed blood, and you can see that if we were able to bin X-rays according to energy, then we could take advantage of the K-edge absorption and increase dramatically the contrast for these materials. And so starting out in trying to develop a detector for CT, a modular design has been used because, as you'll see, with all of these detector technologies, modules need to be formed with little dead space so that they can be tiled together to form the large fields of view that are required. In the particular designs used for CT, I used cadmium telluride as the direct conversion semiconductor, which is coupled to ball grid arrays, which have packaged application-specific integrated circuits. And then these have a digital output of the number of counts and their energy, which is taken out of a standard DAC setup. And so taking a look at the technology for CT, the first system was made using two energy thresholds, which means that this is going to be capable of counting each X-ray and binning them into two different energy bins, a low and a high energy bin. So you can see the schematic diagram of the circuit, and this was implemented in silicon, in an ASIC, and packaged inside a ball grid array here, as shown here. And then here you can see a digital readout system is used, which is vertically integrated underneath the sensor area. So both the ASIC has to be vertically integrated underneath the sensor and a readout system as well. So looking at an edge view here, you can see by achieving full vertical integration of all of the electronics, you can then tile many, many of these modules together to create the fan beam geometry that's used in CT. These detectors are first tested in an X-ray cabinet before being used in a system to image patients, for example. And so here we can take a look at the output count rate ranges and the energy resolution that was achieved in this first dual energy CT technology. And we were able to achieve an output count rate above 5 million counts per second per square millimeter, and with a dynamic energy response up to 140 keV, and with an energy resolution of about 6 keV full width half max. Here shows a field of view, a flat flood uniformity for one particular module, and if you'll notice that there are less counts in the pixels that are around the edge, that's because I make the pixels that are around the edge smaller than the pixels in the center, so that when they're tiled together, the small gap that's between modules will not disturb the preserved pixel pitch across the entire field of view. And so here's a picture of the cadmium telluride, and it's also important to be able to use cadmium zinc telluride because of the availability of these materials having only been developed in the last decade or so. There's very few sources. And so cadmium telluride and cadmium zinc telluride can be used. The cadmium telluride and cadmium zinc telluride have a different bulk resistivity, so that there is a much larger dark current in cadmium telluride. Because of this, when you see SPECT and PET systems being developed using cadmium zinc telluride, which is also often called CZT, it's only used and cadmium telluride cannot be used for those applications, and that's because the peaking time to integrate the charge from each X-ray that comes in is sufficiently long, and so that the dark current that comes from the thermal current contributes to the signal. But when you're doing very, very fast photon counting, you use a peaking time of only a few nanoseconds. And in that case, the dark current doesn't contribute to the noise, but rather only the stray capacitance contributes to the electronic noise in the system. And so in these type of systems, you can use both cadmium zinc telluride and cadmium telluride, provided that you minimize the stray capacitance on the input of the preamplifiers. Here also I show that you can obtain the same energy resolution from both materials, from cadmium telluride and cadmium zinc telluride, in this case about 7 keV full width half maximum at 60 keV for americium sources. And so this module was used to populate a GE Lightspeed system to create the world's first full photon counting spectral CT system to image patients. The final module that was built is here on an aluminum bar, which was designed to be the same shape of the substrate that held the previous integrating detectors that are normally used, so that they can snap into place into the conventional CT gantries that are used. And here I present the first patient images using a spectral photon counting system, and we can see the advantage of using the photon counting system. So this is a neck study of the carotid artery, and normally this would be done with a non-contrast scan would be done, and then there would be an iodine contrast injection, and then a second measurement would be made, and those two images would need to be compared or subtracted from each other to separate bone and iodine. which have similar attenuation. But in this case, a single scan can be used, and by binning the X-rays according to energy, we can identify the iodine and then subtract it from the image. So you can see that as the energy increases, right, then the iodine goes away and the bone stays, and in this case this would be a plaque or a stenosis. And so then you can take a look at the left side shows the contrast enhanced neck image. And this is what you would get under contrast, where you can't distinguish between the iodine and the plaque. But in the right side, we make a virtual non-enhanced image by subtracting the iodine that was identified in the energy resolved images. And you can see that this occlusion is probably not significant enough to require treatment. So that's good news for this person. And also, the data that you get from these type of detectors can be rendered in the same way that the data is rendered from conventional energy integrating CT systems. And shown here are some results, in particular, the virtual endoscopy is a very good result that you cannot obtain with conventional systems. And here is the results of an abdominal study that is done. And in this case, you would have maybe 3 scans. You'd have a non-contrast scan, and then a contrast scan, and then wait a certain amount of time, and then do a washout study. But in this case, again, those 3 scans can be replaced with just 1 scan, since that we can identify the excreted contrast, subtract it from the image, and see that this calcified structure is probably not going to need to be treated. And so this first system was sufficient for neck and for abdominal studies, but not sufficient for cardiac CT. In cardiac CT, the flux from the X-ray tube is much, much higher. The tube current is usually changed from 120 to 200 milliamps up to between 400 and 800 milliamps to be able to acquire an image fast enough to freeze the motion of the heart. And so we performed a Monte Carlo simulation using the standard cardiac MCAT phantom from Johns Hopkins to determine what the attenuated beam count rates are. And although most are between 1 and 10 million counts per second per square millimeter for the attenuated beam on the detector, in the case where the beam misses the sternum and the rib and the heart and passes through the lung, you can get output count rates that are up to about 20 million counts per second per square millimeter. So a detector technology was needed which could achieve a much, much higher count rate. And one way to do that is to reduce the pixel size, and another way to do that is to increase the peaking time. And so I worked to develop a system with 0.5 millimeter pixels, and which uses a much, much faster peaking time to obtain a higher output count rate. Here I show a shape of the pulse with a 100 nanosecond shaper, and the rise time, we need to acquire at least 80% of the signal, and that can be done in 10 nanoseconds. Here also we show cobalt spectra. And so also it's important to move beyond dual energy methods. So dual KVP CT is becoming more and more popular. It's because it can increase material specific contrast, and it can also reduce the dose by optimal energy weighting of the different energy images. Although 2 is good, 4 is better. With 4 different energy bins, we can target new applications, such as the K-edge imaging of nanoparticle contrast agents. such as gadolinium bismuth or gold nanoparticles. And these nanoparticles are being developed which have function. And if we can then image the nanoparticles by doing K-edge image, then it's going to be possible to achieve functional CT for the first time. Here's a picture of the new ASIC. In addition to making new smaller pixels in the cadmium telluride or the cadmium zinc telluride, it was also needed to go to a new architecture of the ASIC in order to keep that stray capacitance that I was talking about very, very low, to keep the electronic noise low. The ASIC needs to be very physically close to the pixel itself. And the only way to do that with these small of a pixels is to go to a two-dimensional ASIC, which is done and attached to the sensor directly by a flip chip bump bonding method. Over here we see the achievement of the flip chip bump bonding on this small length scale. And so this increases the output count rate up to 20 million counts per second per square millimeter, and also provides a linear energy response across the entire dynamic range for CT. And also, an important point for any detector physicist is that you would notice that the full width half max energy resolution is the same across the entire dynamic range. This is only possible if the noise in the system is dominated only by the electronic noise. And here you can see a picture of the full ASIC, which has 16 by 16 inputs or channels. And this ASIC was first tested by wire bonding it into a ceramic package. It also becomes impossible to calibrate these systems unless there's an automated method to do this. Now, each channel will have a slightly different offset and a slightly different gain. And the only way to compensate for that would be to adjust the offset at a particular different energy. And so here you can see the pulsar response. This would be integrated spectra. So differentiating this step function produces the delta function-like response that you would expect from a pulsar input. And so by adjusting the offset, by adding a small voltage with a trim DAC, a digital to analog converter, inside the ASIC on each channel, we can program the amount of offset that has to be added to each channel so that we get the same energy response. Now, the detector does not have a perfect response, otherwise the step function would be completely vertical. There is electronic noise in the system, and if you differentiate this, you would get a pulsar peak that had some full width half maximum. In the literature, you will hear people talking about how these photon counting detectors have no noise. That's not true. They have no dark noise, meaning that there is no signal if no X-rays are present. And that's important for very low dose methods where we are pushing down the intensity to near where the dark current is in regular integrating detectors, and then that becomes a problem, and that problem is eliminated with the photon counting method. Here we can see a comparison of the 0.5 millimeter pixels and the 1 millimeter pixels. One of the disadvantages of using smaller pixels when doing direct conversion in semiconductors is that you get additional tailing from charge sharing because there will be a K escape from fluorescence that occurs in the direct conversion of the X-ray energy into electrical charge. And so with this system sped up as fast as possible, we achieved an output count rate of 23 million counts per second, which had only a loss of 15% and a linear response up to 14 million counts per second per square millimeter. So we're getting close to achieving a linear response over the entire counting range, which is required for cardiac CT. and this was done in 0.5 millimeter pitch cadmium zinc telluride. Here you can see the energy response is linear to 140 kVp. That takes care of the problem of the dynamic range, whereas this previous slide takes care of the problem of the counting range. So those two things are achieved. And here you can see that we took a look at spectra, and this is X-ray spectra measured at 1, 5, 10, and 17 million counts per second. And you see a little bit of pileup. Pulse pileup occurs when two X-rays hit the detector within one peaking time and can be recorded as a single X-ray with larger energy. Although when we get near saturation at 23 million count, you can see that the peak shifts due to the pileup effect. But this shows that the device can be used well, at least up to 17 million counts per second per square millimeter. Here is a difference versus mean for the stability, which is one of the most important parameters in a detector for CT. And we see no variance in the output outside of statistics. And so, again, a module design which is vertically integrated has to be made with this new detector and this new ASIC. And that is currently in progress. So right now we're trying to build this second generation module to completely vertically integrate all of the readout, and we'll populate these detectors into a clinical system and do some patient imaging. In the meantime, we have encountered a lot of resistance in the industry to adopting this new technology. The major CT manufacturers have recently spent tens of millions of dollars developing new scintillators, like the gemstone scintillator that's used in GE systems. They do not want to just abandon this. They need to make back all that money. And so one way that I think we can force them to adopt the new technology, which will be better for patients, is to bring new applications that cannot be performed with the existing systems, but only could be performed with these systems. And one of the ways to do that would be to bring nanoparticle imaging into the picture. So here you can see some Phantom. Phantom was made with millimolar concentrations of nanoparticles in cylinders inside a cylindrical Phantom, including gold, bismuth, iodine, and calcium carbonate. And here you can see that by using 4 different energy windows, we can separate and identify and image the individual elements separately using the K-edge method of placing an energy window above and below the K-edge of the particular material, and then subtracting those 2 images, and then you'll pick up a large signal increase across that K-edge. So this was done in a preclinical system, and we've done some imaging in a murine model, or a mouse model, to go beyond phantom imaging, and it's done in a orthogonal system using a conventional energy integrating detector to demonstrate that we're not losing any of the other performance quality factors by moving to this new method. And so here you can see some results of this imaging. We have iodine, gold, calcium, and all images put together, because once we have made the separate images, we can false color that image and then superimpose the images on top of each other. So we can now produce color images where the different nanoparticles or different tissue types can be presented all at once. So there's another application. This is probably a lot more exotic and a lot farther away from the clinic, but phase contrast CT has received a lot of attention in the last 10 years, and currently all of the phase contrast CT systems have to raster scan a pencil beam across the object, because the gratings that are used to set up the phase contrast conditions are a function of the intensity is a function of angle and energy, and without measuring the energy of each X-ray, you can only do it in line. And so at PSI Institute in Switzerland, we made some curved diffraction gratings to open up the field of view into a fan beam, and then use the energy resolution of the detector to account for that energy change out of in line, to be able to produce phase contrast images. So here in some phantom images here, you can see a phantom here, and this contains water, and it contains water and water plastic. And so water and water plastic cannot be resolved using attenuation-based measurements, because the Hensfeld unit is the same for the water and for the plastic. And so down here you can see in the you can see in the absorption images, you cannot distinguish between the water and the water plastic. These two holes in this rod phantom were plugged with wax at either end so that no water would go in, and also here in two places over here, smaller holes. But in the phase contrast, where we detect the index of refraction of the material across the entire object, you can see that we get and can resolve these two objects. Okay, so this photon counting method, it's not just applicable in CT. It's also applicable in spectral X-ray absorptometry. Now, this application is usually done for bone mineral densitometry, or also body mass index scans. So BMD or BMI imaging is done. Now, this is traditionally done in a dual KVP method, where two scans are done with two different tube settings and filters to create a high energy and a low energy beam, and then those two images are subtracted from each other. But if we can do the photon counting and count every individual photon and bin it into different energy bins, then all this can be done in one scan, which reduces dose for the patient, and it also reduces scan time. And so here is a picture of the detector made for spectral X-ray absorptometry. It uses cadmium telluride. Now, BMD and BMI imaging is a scanning method, so we don't have to vertically integrate the readout, but the readout can be lateral since it's a scanning method. And then you can see that the readout here is not vertically integrated underneath the systems, but it's laterally integrated and comes out the side. This makes a compact system that can scan the patient without being really hard to place the patient in the system, for example. So in this system, we have an output count rate up to 1 million counts per square millimeter, which is sufficient for the tube currents used in this application, and a linear energy response up to 80 keV, which is also fits with the dynamic range for that application. Here you can see a flood, and again, in the long line, which we make so that we can scan the long bones of the patient in one direction, we use smaller pixels in between the crystals that we place so that the pixel pitch is preserved. These systems have a Very, very, very good energy resolution, and this is important. The energy resolution requirement for BMD imaging is much, much higher than it is for spectral CT, and so we have 1.7 keV full width half max. I think this is a record energy resolution for an area array. Cryogenic single cell elements can achieve better energy resolution, but not in a room temperature device with an entire array of pixels. And here is a barium spectra showing again that by eliminating any noise in the detector, we only have noise in the readout electronics, and so the full width half maximum is the same for all these photo peaks, all the way from 4.3 keV up to 81 keV. It covers the dynamic range. Here we can see spectra. Now this is a samarium simultaneous absorption and emission spectra created by taking a samarium filter and placing it directly on top of the detector to catch the fluorescence. Here you see the K alpha and the K beta peaks for the samarium, and you can see that at very, very high output count rate, near saturation, there is a shift to lower energy. Now, the reason there's a shift to lower energy here is it's not because of pileup, it's because of the use of a bipolar pulse shape. And so with a bipolar pulse shape, which is better in this technology, at very, very high count rates, the baseline can be dragged down, and all of the energy bins are measuring the energy of that pulse height relative to that baseline. So as the flux gets really, really high, the baseline starts to shift down. Okay, and here you see a detailed picture of the ASIC here, and it uses a linear array of inputs, not a 2D array of inputs as in the CT system. And this detector is in the Stratos DMS, the Stratos DR system, which is provided by DMS. This system is doing really, really well. It competes side by side with the GE IDEXA system, which is a much, much more expensive system. Here you can see some patient results. You can see some examples of some hip imaging. This is what the fully integrated image looks like with a conventional integrating detector. This is what the image looks like with the photon counting detector, where we can identify non-bone and subtract it from the material. Also, the high resolution of the detector lets us do cortical bone imaging in the spine. Okay, and so I want to talk now about a third detector technology that's under development to try to bring spectral photon counting into mammography. Now, this is a place where this method can really, really have a lot of impact because it's exceedingly important to get the dose as low as possible. And when the dose is low, the dark image that occurs from conventional detectors is a significant detriment to image quality. So the photon counting method can eliminate that dark noise in the image. It can allow us to push the tube currents even lower and still obtain a good quality image. But there's a problem with mammography in using cadmium telluride or cadmium zinc telluride. The pixel sizes have to be very, very small. The pixel sizes cannot be bigger than 100 microns. And the charge sharing that I showed, which produces excess tailing, makes it that you cannot use those materials, cadmium telluride and cadmium zinc telluride. But we can use silicon. Silicon does not have this charge sharing effect at these energies, okay? But silicon has a very, very low Z, so it doesn't have a lot of stopping power for X-rays. So we need a very, very thick piece of silicon. A centimeter thick would be nice because it would have a good DQE for the tube current beams for the beams that are used in mammography. But you cannot make silicon junctions that are larger than a millimeter. because you need to fully deplete the silicon so that you can collect the charge that's generated. So what we do here is we use an edge illumination. Now this has the advantage that the charge is collected across the narrow junction, so we can use very, very fast peaking times to collect the charge very, very quickly. But by using an edge illumination, we still get a lot of silicon to have a high DQE for the X-rays. Silicon strip detectors have a guard ring around the edge, and the guard ring around the edge creates a dead space in silicon, so it's not directly edge illuminated, but edge illuminated at a slight angle. Philips introduced into the clinic last year the first spectral photon counting system. Well, no, they introduced a photon counting system by using a similar method with a single energy bin. So this cannot do this multiple energy imaging and the nanoparticle imaging that I've been talking about. It has just the single advantage of eliminating dark noise, dark noise from the image. And so it counts photons but doesn't measure their energy. And so here you can see a picture of silicon strip detector with associated ASICs on either side that are connected directly to the silicon wafer by wire bonding. And here you can see an array of these silicon strip detectors that are tiled into a larger field of view. Here the output count rate again is up to 1 million counts per second per channel. And in this case, since the pixels are 100 by 100 microns, this represents 100 million counts per second per square millimeter, which I believe is also a record for the rate at which X-rays can be counted and binned into energy bins. Here is a flood image at 50 millisecond exposure and at 200 millisecond exposures for 50 kV beam and 6 milliamp. At 60 centimeter distance, so much lower tube current that is used in conventional mammography, but we can do that because we don't have the dark noise in the image. Here you can see the energy response. These are the integrated spectra for different kVp from 12.8 up to 30 kVp. Here we can see a noise floor at 4 keV and a linear energy response all the way up to 50 kVp, so that's suitable for mammography. And we see a full width half maximum from a cadmium source at 2.2 keV. Okay, and so I took this prototype and installed it into a system at Samsung and scanned breast here to produce this, and this is at about 6 times lower dose than for conventional mammography, which is at about 6 milligray. This was taken with less than a milligray of dose. One of the challenges that we're working on right now is that with the silicon strip detectors, we cannot use smaller pixels and tile together to preserve the pixel pitch, so there are small gaps. The very, very small gaps you can see as a small line in the image. Unfortunately, in mammography, because of the need to detect microcalcifications and their geometry, this cannot be interpolated over. So currently we're working on a method of laying the silicon strip detectors on top of each other in 2 lines and scanning to eliminate the gap. Okay, so in conclusion, we have achieved an output count rate to 20 million counts per square millimeter for CT with a noise floor of 16 keV and a dynamic range between 30 and 140 keV. So you see that that covers the dynamic range for CT and an energy resolution of 7 keV. For spectral X-ray absorptometry, we obtain 1 million count per second per square millimeter, a noise floor of 4 keV, a dynamic range between 10 and 80 keV. This again satisfies the need for this clinical dynamic range for these clinical scans, and an energy resolution of 1.7 keV. And finally, for mammography, we've obtained 100 million counts per square millimeter, a noise floor of 3 keV, dynamic range between 8 and 60 keV, and an energy resolution of 2.2 keV. The work is funded by NIH grants, and thank you very, very much. That's a very good question. That's a very, very good question. Inside the circuitry, after the pulse goes up over and triggers the threshold to count the X-ray, that threshold cannot reset until the pulse comes back down. So by shortening the peaking time and causing the entire shaping time, so by decreasing the peaking time and the shaping time so that we use a near Gaussian pulse, then we can reduce the dead time. But your point is very, very good. At higher energy, there's a slightly larger dead time than there is at the lower energies. But as long as the peaking time is fast enough, it won't depend on the rate, so it will depend on the energy of the X-ray rather than on the rate. And so I'm working to try to introduce a threshold resetting element to the circuit to be able to force a reset of these thresholds to eliminate the dead time that you're talking about. And I believe I can get that dead time down to less than 6 nanoseconds. And hopefully that will go away, that problem will go away.
When you started talking about the spectral analysis detectors in connection with the bone absorption work, etc., you said that this reduced the dose, and I wasn't quite sure why, because presumably if you sort the image into energy spectra, your counts are very much lower?
That's another excellent question. That is another excellent question. If we all know that in radiography, we're limited by statistical noise. And he's saying that if we take this one image where all of the X-rays are there and we break it up into 4 different images, then the statistical noise is going to be worse in each one of those images. So the images cannot be viewed alone. If they're viewed all alone, there's a lot of quantum noise in there. So the images need to be added together with an optimal energy weighting, which has a small penalty. And so if we optimally weight each one of the 4 images with an optimal energy weighting factor and then add them together, it will bring out a contrast of a particular object, and it will reduce that quantum noise because we've added the images together. But you do pay a small penalty because anytime you take and you add together or subtract, 2 statistically independent data sets, then there's a small noise penalty that is paid there. Thank you.
Any other questions? Okay, I would like to invite Dr. Davidson to facilitate Dr. Barber with keynote certificate.
Great presentation, thanks.
Thank you very much.
I've got too many questions, I won't.
Afterwards, I would love to. Thank you.
I would like to call